Have you ever really stopped to think about what's happening inside your phone or computer? You know the magic behind the scenes? Well, today we're going to pull back that curtain and look at the silent, incredibly powerful engine that makes everything work, the operating system. I mean, really think about it for a second. You click an icon, right? And in a blink of an eye, a whole app just springs to life. It feels like magic, but I promise you, it's not. It's actually a super fast, super complex dance of instructions, and we're going to break down exactly what's happening in that tiny split second. Okay, so first things first, how do we even tell a computer what to do? Well, it all starts with what we call the user interface, or just UI for short. You can think of it as, well, it's the language we use, right? It's the collection of buttons, icons, and menus that let us communicate what we want to the machine. You know, back in the day, there were really two main ways to talk to a computer. On one hand, you had the command line interface, the CLI. This is that classic green text on a black screen you see in movies. It's incredibly powerful for sure, but you have to know exactly what to type. A single typo and nope, doesn't work. It's got a pretty steep learning curve. And that's exactly why most of us today use a graphical user interface, or a GUI. With a GUI, you've got your mouse, your icons, you can click and drag things. It's just way more visual and intuitive. It basically opened up computing to, well, everyone. And of course, we didn't stop there. That interface has just kept evolving. We went from the good old mouse and keyboard on our desktops to just using our fingers with taps and swipes on our phones and tablets. And now we're just talking to our devices. Hey, set a timer. The goal has always been the same. Just make talking to the machine feel as natural and as human as possible. All right, so you've used the interface, you've clicked the button. What happens now? This is where the star of our show, the operating system, steps in. And honestly, the absolute best way to think about the OS is as your own personal, super efficient digital assistant. Its entire job is to take your simple request and then handle all the messy, complicated details behind the scenes to make it happen. So how does an app actually talk to this assistant? Well, it uses something called a system call. This is the official, formal way a program asks for help. It's like the app raising its hand and saying, "Excuse me, Mr. Operating System, I need you to do something for me." It's asking the very core of the OS, this part called the kernel, to perform a special task it's not allowed to do on its own, like, say, accessing your camera or saving a file to the hard drive. Let's make this super concrete. Imagine you're just dragging a file to make a copy. To you, it's one simple action. But underneath, whoa. That one drag sets off a whole chain reaction of system calls. The program asks the OS, "Hey, can you find the original file?" Then, "Okay, now can you create a brand new empty file?" Then it's this back and forth loop. Read a little bit from the first file, now write it to the new one. Read a little more, write a little more. Over and over, incredibly fast, until finally it says, "All right, we're done, close them both up." What we see as one smooth progress bar is actually this frantic, high-speed conversation happening completely out of sight. And that right there is the whole point. This incredible complexity is hidden from us on purpose. We're not supposed to see all those system calls flying back and forth. We just see a nice, simple program with a progress bar. We're interacting with a friendly application that's basically acting as a shield, protecting us from all the raw, complicated machinery working away underneath. So what kind of stuff is this digital assistant managing for you all day? Well, the obvious things, right? It's what actually runs your apps. That's called program execution. It handles all your hardware, your camera, your printer. Those are I/O, or input-output operations. It manages your entire file system, creating folders, saving files. It's in charge of communications, like connecting you to Wi-Fi. And it's even the one that tells you, whoops, this app has crashed. But then there's a whole other set of jobs it's doing that are completely invisible. The OS is like a traffic cop for all your computer's resources, deciding which app gets to use the main brain, the CPU, and the memory, millisecond by millisecond. It's also the security guard at the door, making sure a buggy app can't bring down the whole computer or spy on another app. It's this constant hidden management that keeps everything running smoothly, efficiently, and securely. Okay, so we get what the OS does, but how is it actually built? Turns out, not all operating systems are designed the same way. Just like buildings can have totally different architectural blueprints, operating systems have different designs, especially when it comes to building that super important core, the kernel. So for a long time, there were two main schools of thought. First, you have the monolithic kernel. Think of this as one giant single piece of code that does everything. The big advantage? It's ridiculously fast, because all the parts are in the same room and can talk to each other instantly. The downside? Man, it's complex, and if one little part has a bug, it can potentially crash the entire system. The other approach is the microkernel. Here, the idea is to keep the kernel as tiny and simple as possible. It only handles the absolute most critical stuff. Everything else, like file systems or device drivers, runs as separate programs. This makes the whole system way more flexible and secure. But, as with everything in engineering, that flexibility comes with a trade-off. See, while a microkernel is awesome because it's more secure and easier to add new features to, there's a small performance hit. Every single time one of those outside services needs to talk to the tiny core kernel, it's a little bit of extra work, a little communication overhead. And those tiny delays can start to add up. So, which one won? Monolithic or microkernel? Well, the real answer is neither. Or kind of both? Today, pretty much all the major operating systems, Windows, macOS, Linux, are what we call hybrid systems. They've cleverly mixed and matched ideas. They use a monolithic style design for the really speed-critical parts, but they use microkernel ideas for other components to get that flexibility and security. Basically, they're trying to get the best of both worlds. Okay, so all this deep-down technical stuff, this architecture, it actually leads to a really practical question that I'm sure you've bumped into. Why can't you just run a Windows game on your Mac or a Mac app on your Windows PC? Why don't they just work?
The core of the answer, the real reason for this, boils down to a three-letter acronym, ABI, the Application Binary Interface. And you can think of the ABI as a super strict contract, like a legal document that lays out exactly how an application has to talk to the operating system.
And here's the kicker. Every operating system has a different contract. The ABI defines the precise technical way an app has to format its system calls. So a Windows app is written to speak the Windows ABI language. A Mac app is written to speak the macOS ABI language. They are, at a fundamental level, trying to talk to the kernel in completely different dialects, and the kernel just doesn't understand the wrong one. So then, how on earth do we get apps that do work everywhere? Well, developers have a few really clever tricks up their sleeves. One way is to use something called an interpreted language, like Python. You write the code once, and then a special interpreter program on each OS translates it on the fly. Another way is to use a virtual machine. This is like building a little simulated computer inside your real computer, and the app just runs inside that simulation. A famous example is Java. Or the most common way for big apps is they take their main source code and they compile it separately for each system, creating one version for Windows, another for macOS, and so on. And that really brings us to what's next. For decades, the operating system has been our silent, invisible assistant, faithfully translating our simple clicks into incredibly complex actions. But as we head into this new era of AI agents, assistants that are proactive and intelligent, how is that whole relationship going to change? Will we stop clicking and start conversing? Will our devices start anticipating what we need before we even ask? That right there is the next great evolution to keep an eye on.